All right, there are four main information from a proton NMR. Right, similar to carbon. Number one, number of signal, which is the number of chemically non-equivalent proton. That's like carbon. Okay, so if you look at the molecule of ethyl acetate up here, now you can see that there are three types of proton, and I label in color A, B, and C. Okay, and that's why you can expect three signals. All right, very simple there, but it will get a little slightly complicated. But just stick with me, hang with me. Okay. All right. So symmetry. A lot of some molecules have symmetry, so be careful. Let's look at the molecule benzene. How many types of protons are there? Well, there are 6 protons, but all of them look the same, right? They have the same environment, so they're chemically equivalent, so the same type. So you can expect that benzene will give you one signal on a proton NMR, and same thing with carbon. All 6 carbon are the same. Okay. Now look at the molecule of propane, right? Propane got 2 types of proton, blue and red, right? The blue, they are 6. This 6, the blue hydrogen, they are the same thing, and we have the 2 red, so 2 signals. Next one also have symmetry in the middle. Okay, this one got this one should have 2 signals, so 2 type of proton. We have the red and the blue. All right. Now the difficult one is right here. When the molecule have stereochemistry. For example, we got a double bond right here. So if you remember cis and trans in the carbon NMR, similar to that. This compound we have, take a look. 1, 2. These 2 right here, this double bond cannot rotate. So these 2 protons are different. So 1, 2, 3, and 4. All right. To test that, if you're not really sure, you can't really see it. Pick a reference point. For example, I'm going to pick reference point as this methyl group. The blue one is further away. The purple one is closer, cis and trans. Okay, because this double bond cannot rotate. So you can expect that this molecule should have 1, 2, 3, 4, so 4 signals. Okay. Now the stereochemistry. So we have R and S. All right, take a look at this type of compound. All right. I'll have you guess real quick. Just guess first. All right. Just guess. Let's see how many types of protons are there. Then count with me. 1. Don't forget the OH right here. We have OH. This hydrogen show up too. 2. With the one behind is carbon. 3, 4, and 5 and 6. Okay, that's a difficult one. Let's take a look here. So easy explanation. We have a chiral center right here, but forget about chiral center. Every time when I try to talk about chiral center, people get like, oh my god, this is so confusing. No, just forget about chiral center. Look at this molecule. The red proton is closer to the OH, but the orange proton is further away from the OH, right? Because the orange proton is away from you, but OH is closer to is pointing toward you. So this hydrogen is pointing toward you, they're close. Okay, and the orange proton is further away. That's why they are different. All right, I'll give you some more detail in a little bit. I will take a look right here. So on the right side, these are the same compound you saw earlier. All right, we just talked about it. Now on the left side though, how many type of protons are there? Well, if some of you know, so on sp2 carbon, the whole molecule is flat. Now the whole molecule is flat. So the front phase and the back phase are exactly the same thing. And so we have this proton is 1, 2, and 3. Okay. Yeah, look at the carbonyl. Carbon is just straight up. So this think about on a paper plane. All right. So these 2 protons have the same distance to that oxygen. But now you add sodium borohydride. So hydride attack. The OH is pointing away from you. So one of these gonna get closer to the OH, which is the orange proton closer to the OH, and the red proton is further away from the OH. Okay. Now some of you might have a question. If these 2 protons are different, what about the 3 proton outside right here? Should they be different too? Well, here's the thing though. This carbon bond can rotate. I mean, all this can rotate, but let's take a look. Let's focus on the 3 proton outside. You can do on the left side or the right side. You get the same answer. All right. All right. So I'm going to show you this. I'm going to rotate this carbon single bond 60 degrees. Right. The red going to replace blue. The blue replace green. Green replace red. So you get that. And I can do one more time. You get that. All right. I want you to look at this. All these protons will get to the position, to the location that have the same distance to the OH. That. So as this CC single bond rotate, all these 3 protons will rotate right here, right here, right here, and they all have the same distance to the OH. Basically, all these protons are in the same environment. All right, but not the case of a CH2 next to a chiral center. Here's a problem. Let's take a look. Do the same thing. I'm going to rotate 60 degrees. Red proton will replace the metal. The metal replaces the blue. The blue replaces red. You get that. And I can do one more time. Okay. So same drill. Now I want you to look at this. Start with the red proton. When red proton go up at the top position, this location, the OH and the methyl are cis. Okay, the OH and the methyl are cis to each other. But when the blue protons rotate, replace the hydrogen, go up to this location, the OH and the methyl are trans to each other. So basically, the red and the blue protons are in a different environment, even though they can rotate. But they're still in a different environment. So these 2 hydrogen are different. They're chemically non-equivalent. So they're different environment. So they show up different in the different signals. Okay, just count it 1 and 2. There's 2 different signals. Same thing with similarly in the ring system. Look at cyclopentanone on the left side. So this is a flat, right? I just want you to imagine this like a paper plane. Okay, it's just like a paper flat, like on the screen. Now all these protons pretty much. So these 4 protons are the same. These are the same, and these are the same. So 3 different signals. But once you do it add LAH, so you get an OH point up. Now this is not a paper anymore. So paper kind of like curl a little, curl up towards you. So basically, the hydrogen at the front are closer to the OH, and the hydrogen away from you are further away from the OH. These are 2 different now. So the top phase and the bottom phase are different. Okay, so same thing. So we have green closer to the OH, and we have the further away, so the purple further away from the OH. And same thing right here. There's a two different protons. So we have 1, 2, 3, 4, 5, and 6 signals. All right. Oh, 7. I forgot. People usually forget this all the time. Always we have that proton right there. Okay. All right. We're gonna practice it together right here on the next video. Okay.